Okay, everyone. I think we are ready. Gordon is checking the virtual laser. So I just had an idea, kind of a random idea, because it worked so nice last time. I would ask ChatGPT to introduce our guest speaker today. So let's see how this goes.
But you use one of the recent models.
Hey, ChatGPT, can you hear me?
Yep, loud and clear.
So we are here at the AI Bootcamp at Florida State University, and we have a guest speaker today. It's Gordon Erlebacher from the Scientific Computing Department at FSU. Can you please give us a 30, 40-second introduction to him?
Sure. So Gordon Erlebacher is a professor of scientific computing at FSU with a background in plasma physics and computational science. He worked at NASA Langley on computational fluid dynamics and visualization, and later moved into HPC, machine learning, neural nets, and now LLMs and AI in education. So he's very cross-disciplinary and super fluent in technical computing. And lately he's been focused on practical uses of LLMs in teaching and in agentic workflows.
Okay, thank you.
That's pretty
Okay,
pretty
that's
good.
it. Good night. My job is done.
ChatGPT, could you deliver my talk? Okay, that's it. Okay, so today I'm supposed to talk about agentic AI. Okay, so you guys were all here, or most of you were here yesterday. So first let's start with, I'm assuming that everybody has used GPT, Gemini, or Claude at some level, right? Has anybody specifically done agentic AI, or what you think is agentic AI? No, pretty much not. Okay, so maybe you learned something in that case. Okay, so agentic AI. So I'm gonna contrast regular models like ChatGPT or Claude against agentic AI and try to explain what the differences are. Okay, so nothing technical, no math, but the idea is that by the end of the talk to have some lessons learned, which I consider to be very important. Now in here, so the way I did this, I had a talk that I developed for last year for K through 12 kids, for the MLX conference, which we have in February. And last year was on agentic flows, it so happens. And I took this talk and gave it to Claude Code. And I said, take this talk for kids and generate a talk for this audience, with FSU colors, right? And so that's a talk I'm giving, which I've gone through and did some editing, and more conversations. So none of this is generated by hand. So this is just to give you an idea of what one can do with AI. Oh, okay, wait a minute. So I'm going to do this. Okay. So what are you, I'm just going to look at my screen. This is too hard. Okay, so I'm going to want you to, at the end of the talk, I want you to understand what agents are, and then I want you to understand, let's say, the 5 different levels of autonomy. And there will be chemical applications, but I'm not going to simply repeat what's on the slides because you're going to get me on the pronunciation on anything I say. So there's no point exposing myself. I just defer to Ollie and friends. And Tim Logan is in the back there, so he could ask him questions as well. Okay, and then, but what's more important is to find out what you can trust and what you cannot trust for agents. Right? So you got to be very careful when you use these AIs. They can do almost anything, and they can convince you of almost anything, but they can also make a lot of mistakes, right? And the mistakes are going down, right? But the trick is to know where the mistakes are, because you might have only one mistake in a huge document, but if that mistake leads to somebody dying, that becomes an issue. Oh, yeah. Okay, so let's contrast a language model against an agent, right? So in a language model, you ask a question and you get an answer, right? So that defines the question plus the answer defines the context. You heard about context, right? If you then ask the next question, that question gets added to the context, right? So the context now becomes the first question, first answer, and the second question, and then you get a new answer, right? So so if you're discussing chemistry and then all of a sudden you start discussing cooking, and then you return to chemistry, the answers are going to become less good because the chat is doing next word prediction based on whatever you input, right? So that's an important thing to know. Everything also is probabilistic, right? So you have the exact conversation twice in a row. It's actually not possible. The first question asked multiple times will give you different variations on the answer, unless temperature is 0, if you know what temperature is in the context of LLMs. Okay, so there's no calculation, there's no tools, there's no nothing. There's just a conversation. Okay, and in fact, when you use local large language models, which means you can put them on the computer without access to the internet, they have less capability, but they are operating with pretty much the original type language models. Okay, now an agent, okay, has within it a large language model or multiple large language models, but it is more autonomous, right? So you ask the agent, for instance, to book an airline flight, right? So it's going to divide that into a series of tasks, right? And then it's going to execute each task perhaps with a language model or with a database connection or with a phone call or whatever. And you never know in advance what every step of the way is going to accomplish, right? So the phone call may have slight variations, the prices will have slight variations, and so the large language model is going to respond in different ways, right? And by the time you've executed 30 steps, the question is, how accurate is the final answer? I mean, are you actually going to get to where you're going? Are you going to pay a reasonable price, or are you going to get ripped off? I mean, you don't know. Okay. So that's what's written here on the right. And at the bottom, it says, final check is yours. I am the one who underlined final check, not the large language models. So which means that whatever happens on the right side, okay, you are responsible for the final check, right? So I tell my students in class, you can use the large language models. I don't check for cheating, none of that stuff, because I don't have the time to do all that. Okay, I have quizzes, right? So they cheat, they can't answer the quiz, so I don't care, right? But I tell them they're responsible for the result. You could cheat, you can copy from the large language models, you can be creative, but you are responsible for the final result. That makes them think twice before copy pasting. Okay. Okay, anatomy of an agent, right? So you have a model, it can have multiple models, right? Because different models have different capabilities, and you may want to use different models for different purposes, right? And then look at that, a spelling mistake. Okay, you got tools, right? So these tools can be the bash shell. When you type a command on Linux, that's a tool, right? You can have databases, you can have literature searches, you can have citations, you can have research, okay? And then tools can be a robot in your chemistry. You can have a robot in your chemical lab doing something on your behalf. That's a tool, right? So the AI, right? So you talk to the AI analyzes whatever you say, and then comes up with a plan, and then starts executing different tools in different orders to accomplish different things. Those results get fed into one or more models. Those models continue the analysis, and you go on and on and on until you get your final result, which hopefully is correct. Okay. Right, so that's everything that's mentioned here on this slide. And then, and so the whole thing forms a loop, right? So this loop is, you talk to the model executes tools, it makes use of whatever it knows about you. Models these days have memory, right? So for instance, the models now can remember what you talked about a week ago, I mean, depending on how you use the model, right? Then it will evaluate everything it collected, it will take action, and then it will reiterate. And it just goes through a series of loops. And at the end of the loop, it does some form of verification, right? And so verification in this talk will become very important. It's very important, right? So verification simply means that you cannot fully trust anything that's done. And so you got to verify the results, right? And so you can verify once at the end after you spend a lot of money and then iterate again, or you can verify as you go along, right? So the name of the game is how to do verification, where to put the verification. So I'm not going to talk too much about that, but that is a really big deal. Okay. I'm never going to learn. Okay, is this going to work? If I click on something called play, where is there a mouse on here? Oh, my finger. Okay, maybe I just forget it. Okay, so let me just describe it. Oh, just click on that. Okay. Right, so this is just showing the loop, right? So the language model reasons and then acts, observes the results of whatever it came up with, then continues reasoning, and you can see a box for memory. Okay, so it takes that memory into account. Anybody who's heard about RAG, retrieval augmented generation, that's already disappearing. Okay, it was very big over the last 2 years. Okay, that's where you make use of external information, which gets stored in databases. And so the model, which doesn't have enough memory for all this information, can query these databases to get information about what it needs. Because you must always remember, I'm just going to tell you about all these things you have to remember, is that language models are trained, right? These training costs a huge amount of money, like Oliver talked about, but this training uses data as it existed when training occurred. So when you're using Claude, right? Claude finished training maybe 6-8 months ago, right? And so you're using data from the training from 6-8 months ago, right? It's a little more complicated than that. And so the data is not up to date. So you basically say to Claude, what happened in the world yesterday? You're not going to get an answer. But if you add to it, search the web, then you're going to get an answer which will likely be correct. Okay? Okay, so this actually went through. So let me go to the next page. Yeah. Yeah. Okay. So the model as an oracle. Okay. So what do I mean by this? Okay. So you basically go through turns. You supply information. It returns data. I've said this already, and you got no access to anything. However, chatbots are still very useful. I mean, I use them all the time. Okay. Now, at the time in the early days, right, it would actually hallucinate a lot. Hallucination became a very big deal, right? So here on the right, it talks about citations generated. So people, you write your grant, for those who write grants using a GPT, it will generate citations, and then you can count how many citations are actually real and how many are false. And the number of false citations were fairly high in the early days, but then they became more and more accurate. I mean, right now, honestly, it's rare to have citations which are not accurate, but it can happen. And again, it depends on the tool you use. If you use GPT directly, it's not as good as if you use Perplexity. Why? Because Perplexity calls a language model, but it's agentic. So it goes through a verification process, and it can actually self-correct. Okay, that's the thing about agents. And if you have questions, you should just raise your hand and ask. It's more fun that way. Okay, so a lesson to learn is that the AIs, okay, it was very impressive in 2022, 23, when the AIs could speak pretty much the same way, write the same way we do, more or less, right? But over the years, the AIs have become more and more fluent. By fluent, I mean they become more and more convincing. They sound more and more like you, although, they can also use esoteric words which identify them as AI, and so they get better, then they get worse, they get better, then they get worse. It's an evolving thing, but ultimately they can manipulate you much more, right? I mean, OpenAI was sued because they supposedly led somebody to commit suicide, right? So once you hear those kind of stories, you've got to be careful. However, the fact that it's fluent, or the fact that it says it's confident about something, like if you ask the AI, are you sure of your answer? Well, sometimes the AI will actually think some more and provide a better answer, or sometimes it may say it's very confident. But the fact that it's confident does not mean it's correct. Okay, that's an important lesson to learn. Okay, you can never be 100% sure. On the other hand, if I talk to my student, I can't be 100% sure either. Okay, so I always remember that, right? When you're talking to the AI, early days you were talking to an undergrad, then you were talking to a grad, then you're talking to a postdoc, then you're talking to a colleague. That's where it stops, because there's nobody smarter than the colleague, right? But but the point is, the colleague can be wrong. There's always a time in a student's life that you get to the point where you realize that the professor's just a regular human being and makes mistakes, right? There's a period where you think they know everything, and then you reach the period where you realize that's not the case, right? So everybody hallucinates, and so when you ask something of let's say an expert, you've got to evaluate whether it's correct or not. And today we live in a period, in general, where the amount of things which are false is increasing. Let's put it that way. Okay. So confidence is not the same thing as correctness. Okay. So here is various steps, and one can do graphs of, at various levels. Function calling, right? So in the early days of the AI, GPT-4, you had function calling. So basically, you could create your own functions, in JSON, if you know what JSON is, and you could basically say, I want to call a weather service. So you would give the URL of the weather service, and you would say, I want to call the function that says get temperature, and these are the arguments, and this is the return type, etc. And then the model was trained to recognize such functions, right? So in the context, when you would basically say, what's the weather, the AI would know to call that function. It would extract the temperature, it would extract the proper information from whatever you wrote. It would call the function would return a result. That result would be added to the context, and then the conversation would continue. It would be like you having multiple turns of a conversation. That's what would happen. And then the number of functions kept increasing. It became more diverse. And then eventually that led to the first generation of agents. Okay, and this was super cool. But now what happens is that different models created functions with different, let's say, different conventions, right? So when you generate a JSON file that you want the language model to recognize, you're basically saying you file like how the arguments are stored, how the function is stored and defined. All these satisfy certain conventions created by the creators, right? And different companies might use different conventions. So that if you wanted to use different models and call the same function, you had to create all kinds of specialized code to be able to handle these different definitions. And so eventually, something got created by Anthropic. They handle Claude, okay, called MCP, Model Context Protocol, which standardized all this. Okay, so that was a way that would allow you to connect to databases and weather services and telescopes and virtually anything, Notebook LM, right, in a way which was standardized, which means that once you learned it to do it for one service, it became very easy for you to do it for multiple services. And so people started creating packages which could easily be connected to different models from different vendors to access a wide range of tools, right? And so you can see how these tools become useful for agents. Agents use tools, right? They use a mixture of tools and a mixture of models, and different tools have different specializations, different models have different specializations, and all that gets called together. Okay, so that's that. Then you've got A2A done by Google. That's agent to agent. So agent to agent is where an agent talks to another agent, right? Until now, the model talked to, let's say, an end service, to a database which existed in the prehistory age, right? Like 1990, prehistory, right? But now you want the agent talking to the agent, right? So I have a language model. I create my agent, right? And my agent, the dean calls me to have a meeting. So I'm not going to go to the meeting. I'm going to send my agent to go to the meeting, right? My agent is going to go to the meeting on my behalf and return a recording of the meeting and an analysis of the meeting to me. Now the dean is at the beach, so the dean is going to send his agent to the same meeting, right? Now his agent knows all about his previous meetings because it's got memory. We just talked about memory, right? So the agent has a context which is different than the context my agent has. So when they talk, it is not very different from me talking directly to the dean, right? And so the agent's dean will now go report back to the dean on what transpired, and my agent will return back to me while I was doing other things. Okay, so we're not there yet, but I mean, those kind of things do exist. Okay, and so that's agent to agent. And this A2A is a protocol to make it easy for agents to talk to each other. So that, and once you got such a protocol, you're going to get a proliferation of agentic to agentic communication in ways that you cannot necessarily anticipate. So in the way that these days you've got billions of devices out there, which are called, what was it called? Whatever, sensors, of all different kinds. There's billions and billions of those all around measuring all kinds of things, like MEM devices or whatnot. Okay, in the same way, there's going to be eventually millions of agents all communicating and creating all kinds of good things and bad things, because that's always how it is. Okay, so anyway, so this explains this, and of course the talk is not going to end, but you're going to be sent maybe you were sent already, a link to my Google Drive, to a folder which contains the activity for after this talk, but also contains the talk itself. Okay, so it contains more than what I'm going to talk about. Okay, so so this is just a brief chart to explain the difference between MCP agent to agent and function calling, but I think I explained it well enough. So when you look yourself, you can look at this. Okay. So this is chemistry. So I'm not going to say anything on this. Of course, my notes are not there. So, but whatever it is, the chemistry community has definitely been using agents to do more and more sophisticated chemical analysis, okay, including the use of robots. You know, like you want to create compounds, etc., and you want to test out, let's say, 100 compounds. Well, the chemist can either do this over many days, or they can give it to a robot. The chemist can go to the beach, and then the robot can do all the analysis. But again, is the analysis correct? That's another matter entirely. Okay. So on the right, okay, it's basically what the agent did, you know, and the thing to remember is what's in gold at the bottom, and is that while the model which used tools gave the correct answer, a chatbot which was posed with the same chemical problems, right? These did not require robots. You know, a model, right? You did this kind of exercise just now. A chatbot which was given the chemical problem to solve sounded more fluent, right? The answer sounded cool, sounded great. You know, you're reading it, it made perfect sense, but it was viewed as being less correct. Okay, so again, correctness, I mean, smoothness does not imply correctness. Okay, some of you may have heard of co-scientists. I certainly didn't, but again, it's an agent used in chemistry. Okay, and you know, or you know, so you can read yourself what's on the top line, and some of you will have heard of this, right? And the bottom line is it made some mistakes, but like it says it's code called the heater shaker by the wrong name, you know, the wrong technical name, but the agent was looping, and the loop, during the loop process, the agent was able to figure out that it used a wrong name for the shaker, accessed documentation, and then was able to correct itself, right? So the agent was a self-correcting agent, and more the agents can do this. So a lesson to be learned is that when you use agents to do anything, to do tasks, you have tasks you want to do, you want to think about how to verify whether the tasks are done correctly, right? So for instance, if I say to you, if I were to ask you or do a plane reservation for me, right? I would say the price should be between in my mind, I would say the price should be between $2,500 and $3,000, but I wouldn't tell you necessarily. And then when you come back with the result, I can apply my verification to what you provide me with, and then make an evaluation as to whether you're correct or wrong. So if you can find ways to provide checks and verifications which lead to numerical answers which can be determined to be correct or wrong, right? Then you've got the possibility of creating agents which loop, you know, which can self-correct. You know, they can keep looping either a fixed number of times or until all checks pass, right? Now, the problem with loops, of course, is that at the moment, they can end up being expensive. Okay, so this is just a picture I got off the web of co-scientists with the robot here. So for those of you who have heard of co-scientists, you would have seen this at some point. Okay. So now the question is, how long can an agent work alone, right? So when you create, okay, so I already said, when you ask a question to a model, the model might provide a right answer these days 9 times out of 10, but then you got one time it gives you a wrong answer. The answer could be completely wrong, or it could be slightly wrong. Like it could say, I'm a woman, if I ask what's my gender, you know, that's very wrong. But if I say, what year was I born, you know, instead of 1957, it might say 1956, and that's maybe slightly wrong. Okay, so errors can be very detrimental, or it can be slightly detrimental, right? Now, like with making airline reservations or creating an organic compound, that I know because I did in school, okay, an organic compound, right? It takes many steps, right? And so for every step, you have a 10% error, and then you have 10 steps or 20 steps. By the end, from a statistical point of view, the chances of your 10 steps producing the right result is fairly low, right? So in order for a process with a reasonable number of steps to execute properly, it's important that each step have an error which is bounded by a rather small amount, right? So the error, yep.
That has, let's say, 10 steps to it. Would it be better than to ask it to do each of those steps individually, or ask all of them at the same time?
No, hold on. Asking them, all of them at the same time, I am translating that to mean in parallel, at the same time. Is that really what you mean? No, but sometimes that's possible, but sometimes it's not. Like if you say, for instance, I want to grade 10 homeworks, I can grade them all 10 at the same time, and I can give one homework to model one, I can create copies of my model 10 times and have on 10 computers and have the homework graded all at the same time. Or I could do it sequentially, and then it would take 10 times the amount of time. But if you're doing an organic compound, okay, there's a specific order. You can't just do anything at any time, right? I don't know the technical terms, but you can't do them. You can't do all steps at the same time when you're creating an organic compound. So, now sometimes there are sub steps that can be done at the same time, in which case the answer is yes. So in general, I would say no. In general, it's sequential, and then you can accelerate by doing certain steps which are not dependent on each other in parallel. Yeah, but if you have if step 5 depends on step 4 and what comes before, then you have no choice. If an error occurs between step 1 and step 4, step 5 will be based on that error. So the error is not corrected by the time step 5 is executed, the error will amplify. Or either amplify or propagate, Okay, so the point is, you need the error for each step to be sufficiently small, statistically speaking, so that by the end, if you do the experiment 10 times, that the total 10 steps will be correct 8 or 9 times out of 10. Okay, so there's a benchmark which says this, right? So you create a benchmark to create some kind of complex process which has, let's say, 10, 20, 30 steps. I don't know the details, right? And then you basically run it, let's say, 100 times, and then you ask how many times were the 10 steps successful, right? And so let's say you run it 100 times, and maybe it's successful 70% of the time, or maybe it's successful 10% of the time, right? And it takes a certain amount of time to run those 10 or 100 steps, right? So the question is, how long can these agents work to do multiple steps in such a way that there's a 50% probability of success, right? So the objective is to be able to run many steps, but with 50% probability. Well, in 2025, you cannot run an agent more than 1 hour. So what do I mean by run agent? If you basically ask Claude Code, let's say Opus 5, and people have done this, to create a game of Minecraft for you, or to create a simulation of you flying around the earth, and so that you can actually see the mountain ranges and fly in, etc. And you ask Opus to create this for you, and to go online, find satellite pictures, construct all the height maps, construct all the objects, etc. You create a prompt. Your prompt is 1 page long. Today, Opus could run for 2-3 days in one shot, and then give you your simulation. You can just imagine the number of steps it needs to do this. It's not like it's doing everything in memory, right? Okay, well, I'm just saying that in 2025, the length of time it could work was 1 hour to get 50% chance of success. Today, let's say early 2026, 12 hours. The time is increasing rather rapidly, right? So we're not far off from being able to run continuously long things. So you can imagine an AI organizing your life and keeping track of all kinds of things. It's exciting and scary at the same time. Okay, just say, okay. Right now, interestingly enough, if you ask for the probability to be 80% as opposed to 50%, right, there's not been much progress over the last year and a half. For reasons I do not understand. I mean, that's something I would want to know more about, because I find that hard to believe. And again, because this slide was generated by AI, I didn't go out of my way to check everything, right? this might be true, it might not be true. Okay. But the 12 hours, I knew. By the way, at the bottom, there's various references. And at the end of the talk, I told the AI to go verify all these references, and it found several errors, and then corrected. Okay, so again, these are 3 different levels of chemistry applications, which I'm not going to get into. That's how I catch up on my time that I spend on these other slides. Okay, but you go from taking a natural language chemical query that gets executed, and then you can evaluate how well it works and how well it doesn't work, versus let's see, what's the second one? Yeah, the second one is actually creating an experiment, right? Which is more difficult than just solving a problem, right? And then the third one is actually creating a paper. Yeah, think something related to papers. You can look at the PowerPoint, which I provided you with, and there's detailed notes with the PowerPoint, so you can learn more about it. Okay, so how the AI create this, right? Every one of these steps is a subset of the next one, right? So at the bottom, you've got chatbots, right? And then you've got tool use, that's function calling. Then you got the agents, which can actually work where you can actually call 3, 4, 5 steps of an agent. Then the long-term horizon is where you can actually talk dozens and dozens or hundreds of different steps, and it still works, right? Those are the ones which run for these, at the moment, days, right? And then at the top, you've got multi-agent system, right? So that's like my agent talking to the dean's agent, right? So you got agents which come from vastly different vendors, different specializations, different uses. Like you can imagine you're developing a chemistry code, right? And at some point, normally you would go consult an encyclopedia, or let's say some specialized documentation on a specific chemical process, right? But you wouldn't do that in a year. You won't do that anymore. You're going to just basically go to your organic agent and consult with the organic agent. So instead of consulting with the book directly, you consult with the agent who can go search Scholar and go search the archives and go search the specialized books to find what it needs. It's got a much higher chance of succeeding than by you telling the AI to go search a specific level of documentation, right? So this is why you would want to use a specialized agent as opposed to using a tool, for instance. But of course, you can imagine if errors propagate with a regular agent and the consequences, the minute you start working with multiple agents, it gets harder, right? Now, the question is, what's a multiple agent? Okay, what's on the next slide? I forget. Yeah, so you got different systems, right? So here's the system on the left is the system with one agent. Okay, so one agent, you're using Cloud Code and you say, write me a function to calculate the factorial. Okay, well, there's something actually doing the calculation. The model's doing the calculation, but the model is within an agent. So the agent does the factorial, it runs the factorial, and then it may create a test to check to see that the factorial is producing the answer it should. Factorial of 5 is 120, right? So it's gonna execute the code with 5 as an argument, check the answer, and if it's not 120, that agent is gonna loop and fix the code, right? But it's still a one-agent system. Now I can create an agent that actually write me several pieces of code, but instead of having one agent do it, this agent is a spawn of sub-agents, right? So my model is going to start executing, it's going to say the other model, start executing these subtasks, and that way the main agent may be free and can keep answering your questions. And then you could tell the main agent, I've got a question for you, and that way the agent can copy. It's the difference between synchronous and asynchronous calculations if you do regular coding. Okay, and at that point, you've got the main agent and then you got sub-agents, but it is still not called multiple agent because, and a lot of people get confused, right? A lot of people call that multiple agents, but it's not. Why? Because the main agent still controls everything. The main agent has information about what's happening in the various sub-agents, either in full form or in summary form, and the main agent can still decide to stop the entire calculation if it wants to. right? If the main agent says stop, or if you log out of Claude, everything stops. But if my agent is communicating with the dean's agent, even if my agent is, okay, but keep in mind that I'm not the only one at the meeting, right? I mean, Oliver is at a meeting with his agent, right? So I've got Oliver's agent, my agent, and his agent all talking to the dean's agent, right? And if my agent decides to leave the meeting and to terminate, the meeting is still going on, right? So this is a case, even if the dean's agent decides to terminate the meeting, the three agents are still there talking to each other, right? So this is a case where you got true multi-agents where no agent has full control of what's going on. Okay, so you can see it's like peer-to-peer, where when you download illegal music in the past, right? Who does that anymore? Right? But you download illegal music, right? This music could be distributed across many computers, right? And no computer was the master computer, right? Or it's like when you search for extraterrestrial life, you do calculations on many computers and there's no master computer. Okay, so that's the difference between one agent, one agent, an agent, and let's say subordinate agents, and then a multi-agent system. And the world is going towards multi-agent system. If you actually search for on the web, if you search for the words the agentic web, right? Apparently the web is being recreated, reimagined in terms of agents, where you're going to have millions and millions of agents communicating with each other. Who knows what they're doing? Okay, but okay. And by the way, I forget the names, right? But people have created social media. You may have heard of this when OpenClaw came out. Some people probably heard of OpenClaw. Okay, there was social media where instead of having humans, there were agents talking to each other and communicating. And people were doing that as an experiment just to see what these agents would talk about, right? The fact that you can have a conversation with a chatbot implies that another agent could have a conversation with a chatbot as well. So therefore, agents can communicate. So now if you have hundreds of agents communicating with each other, what happens?
So seemingly they started a religion. Right?
They what?
They started a religion.
Yeah, they started a religion. Absolutely. Yeah. It's time to reread Foundation and Asimov and all these books. Okay, so here's an example I saw maybe a year and a half, 2 years ago, before agents started growing, and it was very interesting. Like people were asking the head of Anthropic, what's the point of multi-agents? I mean, give me an example, right? So let's assume you want to go to a restaurant at night, right? So what would you normally do? You've got your favorite restaurants, and you go, but you might be unlucky. I mean, you can get reservations, but you could still be unlucky. It's not the band you want, and maybe it's too crowded, maybe whatever. Okay, there could be all kinds of problems, right? So what you do is you ask your agent to call restaurants on your behalf, to find, right? And the agent has memory, right? So the agent knows what food you like, and you say, is it the kind of show I'm in the mood for? This is the kind of crowd I want or whatever. And I don't want to go further than 20 miles or whatever, right? So the agent now, not the agent, your agent can give instructions to duplicate itself and start calling the 50 restaurants of a particular type in Tallahassee, right? The agent can call 50 restaurants. It's not like it's got to call one restaurant and then the next and then the next. This is a case where it's done in parallel, right? So the agent calls 50 restaurants. Each restaurant has its own agent. This agent doesn't know anything about you, just like you, right? So it's talking to the restaurant's agent. Now the restaurant's agent knows everything about that restaurant. So everything you need, like what's the crowd, what's playing tonight, what are the prices, et cetera, et cetera, et cetera. That's all known. All that gets communicated to your agent, right? And then your agent feeds that to a language model, which is the main agent, and then gives you a report, right? So you can kind of do those kind of things now, using, a lot of you have Claude now, right? At least this month. And so you can either use it from the command line, or you can use get the desktop application, which you should get, and then you can use Claude Cowork, and then you can do crazy stuff. Like for instance, I created an app like in about 5 minutes to actually give me an HTML report on the latest medical advances in several fields related to my health, and tell me about new FDA approvals. And every week, it creates a new report in HTML format and then just gives me notice. Right? So you can do that, and so you could have it do literature searches, and you could have it do quizzes, you're just gonna have it do anything. Okay, so 2 questions. Right? So confusing let's see. I forget what I wanted to say here. Side effects erodes authority. I forget. That's the problem with not having notes here. I did not anticipate working on another computer. So it's okay. Let me flip. Okay. So there's adding more agents help, right? So that depends on who you ask, and it depends on when you ask. If you notice a lot of dates on here, date from 2023, 24, 25. At the bottom there's the 2026 controlled test, which I asked for. But a lot of people say where there's multi-agents, information is being dispersed. Information is propagating between different agents, and then connections get lost. One crowd believes this. I personally believe that as agents get better, right, the models will get more powerful, and all the different components of an agent will become more powerful, will run faster, will use more tokens, and all this goes away. We're in a period of transition. So a lot of people are complaining, and a lot of people really do not understand. No, I don't mean they don't understand how the systems work. They don't understand how to use the systems. A lot of people expect too much. The thing that you have to remember is that you can never fully trust the result, and the system is probabilistic. The language models do next word prediction, and that is always true. Okay, so you can never be 100% sure of the answer. That's what you really, as long as you keep remembering that, it's fine. Another criticism is the fact that agents typically consume more tokens than a direct chat. But that's because the agents because of how people have constructed them, have built-in verification processes in order to increase the likelihood of information being correct, right? For the models to improve the degree of correctness, there's 2 ways. One is to make improvements on the architecture of the neural nets, which can get quite complex. And the other one is to actually provide what's called harnesses, right? So harnesses is basically a collection of markdown, let's say a collection of files which contain instructions to the AI on what to do and what not to do under what circumstances, right? And the better the harnesses fit whatever you want to do, the more likely the agents will operate with less error, right? So let's assume you have the AI generate a graph of a chemical compound of some kind. Okay, you're going to get some result. Now, if you load a scale into Claude Code, you heard anybody hear about scales? Okay, scales is nothing but text files which contain instructions about specific topics. Okay, so let's assume you want to create mermaid diagrams. It's a particular kind of diagram. Well, let's assume you want to create chemical diagrams. Well, the people who create chemical diagrams, the experts who create illustrations and books, have particular know-how. There's a way to create chemical diagrams which is different than the way you create architectural diagrams of houses, for instance, right? You create diagrams differently. There's a different style, right? And if you can encode this style in a markdown file, in a plain natural language file, and you provide this file to Claude Code and you ask it to generate a chemical compound, the images will be much, much better, right? And you can go online and there's millions of scale files now. And scales were only invented less than a year and a half, 2 years ago, okay? Millions. And in fact, in Claude Code, you can simply say /create scale. And then it's going to say, what scale do you want to create? And then it's going to ask you a bunch of questions. Then boom, you're going to get a scale. Okay, and then you can make a scale ultra specialized. Okay, so yeah. Okay, so the question is, what's the problem with AI agents? Now, I told you one thing to get out of this course is verification, right? So here is a bunch of chemistry-related experiments, right? There's references on the bottom. And some experiments have to do related to lab equipment. Some have to do with, I don't know, space groups. I don't know what that is. Some of them have to do with spectroscopy signals, right? And these different experiments are set up differently. It's like if you have an experiment which is set up as a binary choice, where the answer is either true or false, that means that a 50% success means random, right? If you only have two choices. But if you have an experiment with you have 5 or 10 choices, and right, then random. If you have 10 choices, then the random means 10%. Right? And so the point is these different experiments that get reported in books, they're different kind of experiments, and the success rates vary all over the place. Okay, so why this chart? The chart is because when you're going to look at papers or you're going to look at results or blogs or whatever, they keep telling you about the success or experiments, how successful was it? It would be a good idea to ask, what is the specific experiment that you're measuring? Because otherwise, these success numbers don't mean anything. I mean, you cannot trust it. So what you can trust is if you look at a particular experiment and you measure it you execute it with a series of models over time, as the models get better, then you can see that one of these bars presumably will go from 77 to 80 to 85 to 90% over time, right? So just be careful when you're comparing things that you compare apples with apples. Okay, so, right. So here's a case where in 2023, there was a experiment in a chemistry lab where they created compounds, right? And so 41 novel compounds in 17 days, right? So this was one of the earliest, I'm not saying it was the first, but one of the earliest, let's say, agentic automated system to create compounds in a chemistry lab. Okay, so this was viewed as very novel. It's groundbreaking because you can imagine if this could be done reliably with no error, well, it's easy to imagine the benefits, okay? Whether it's health or chemistry or materials or whatever. Okay, but in 2024, the data that was reported was re-examined and there were errors found. I'm not saying that 2/3 of the results were wrong, but there were errors found. And so the point is, verification was an issue, right? I mean, ideally, what you want is you want agentic and automated systems with automated verification, right? So this brings to mind a question that I was asked at my own prelim oral exam in college long ago. Okay, I was talking about plasma physics on whatever I was going to do for my thesis, and the professor says, how do you know your answers are correct? Well, how do you know your code's going to produce the correct answer? So of course I said, I don't know. Okay, well, you don't know, you never know. Okay, so the point is, all I said is you can produce tests to increase the likelihood. That's what I said at the time, okay? But the same thing is true here, right? You've got to do verification. And if you do the verification yourself, then you can be sure. But as these AIs generate more and more code, it becomes less and less likely that you're going to check everything. You're going to check things statistically, and you're going to develop intuition as to what works and what doesn't. Or you're going to develop intuition on what it is you should check. Or you're going to come up with your own benchmarks, but you can never be 100% sure. Now, I believe that eventually these problems will be solved by automatic verifiers that can be mathematically proved to work. And maybe there will be new programming languages generated which works better with AI than Python, for instance. Okay? And these languages are being created. I don't happen to know them, but verification is a big deal. Okay, fabrication at scale, right? So here's a case where in 2023, there was a large number, let's say 2.5 million papers that were checked. And there were, in these papers, there were 4,000, let's say, fabricated references across 2,800 papers. So that tells you that the references were found using language models and not checked by the authors, right? So if you write grants now, generate references with AI. I do that, okay? But check them. Okay, but in 2026, in 2025 to 26, the numbers of citations that were wrong went down. That doesn't mean that the people were not generating the citations with AI. It just means that the AIs are improving. Or maybe the people are not using AI. That's possible. Highly unlikely. Okay. Okay, so research. Okay, so research in general can be construed as a process which has many steps, right? So when we do research, this can take months and years. But ultimately, if you were to write a notebook, a journal of everything you've done, every step of the way, you would see that your research is nothing but a bunch of steps building on previous steps. Sometimes you take the wrong path and you retract, and then and then you start again. But it's nothing but a series of tasks. And anything that can be described as a series of tasks by a human will eventually be automated by an AI. It is that simple. Okay. And so that is why, even though it's not part of my talk, the skill you should learn, or the skill students 5 years from now should learn, okay, is not so much the chemistry itself, but how to evaluate the chemical results that are being presented to you. Like, in other words, if somebody presents you an experiment, you should still be able to say this experiment is well constructed, is not well constructed, and what should the next steps be. You should be able to do that, but that does not imply that you have to know as much detail about chemistry that you have to know today. That kind of knowledge is going to go away, but you will still have to know about chemistry, and I will still have to know about scientific computing. I mean, there will be knowledge different in the different branches, but the way you think, you're going to be giving instructions at a higher and higher level. It's like in 1700, everybody could do, well, all mathematicians could do Taylor series of sine and cosine and hyperbolic sine and Bessel functions and all that kind of stuff. But who can do that today? I can do sine and cosine, but not Bessel functions. Okay, so the point is, eventually you don't need it for sine and cosine anymore, right? You got Mathematica, Maxima, all these different things. So the same thing true for AI, right? I mean, the grunt work that you have to do in chemistry, like going to the lab and pouring things carefully and doing whatever you do, in my view, that will no longer be needed. But being able to analyze critically to evaluate whether a result is correct or wrong is important. Okay, so another example. Okay, here's a chemical example from one of my tests in school. Okay, so we had this organic lab, right? And the professor, of course, everybody cheats. This is in Belgium. Okay, so everybody was cheating, right? And so the professor had everybody create an organic compound, which takes an hour. Okay, right? And so you do it, but everybody cheated. So everybody said the efficiency of the reaction was like, I don't know, if you cheat, the guy says 95%, whatever. Okay, but the correct answer was over 100%, because the professor, he gave a series of steps in such a way that a crucial step was, he either forgot to put it down on purpose, in such a way that if we followed his instructions, we would get more than 100%. So that was his way at the time to detect cheating. Okay, but it means that the student, I mean, you had to at least realize you're getting more than 100% and then decide what to do. Okay, but the same thing is true here. You got to have to evaluate the results given by the AI and be able to critically evaluate whether those results are believable or not. Okay.